Hello physics students, this is Dr. Brenzi and this is lesson 7.2.1. In this lesson we're going to be able to describe the motion of a mass on a spring and define important properties of that motion. It turns out that not only do masses on springs but a lot of other objects exhibit similar motion to this, and it's so common in the physics world that we give it a common name, and we're going to figure out what that name is. But first, let's revisit Unit 2 when we were talking about spring forces and refresh our memory. Whenever we have a mass on a spring, we know that the force that the spring exerts on the mass is equal to negative k times x, where k is what's called a spring constant, which measures the stiffness of the spring, and x is the distance that you move the object from its equilibrium point. So if the mass were at equilibrium right here, and if you were to move it down here, then this displacement from equilibrium would be our distance x. Now, one other thing to remind you about spring constants is that the higher this number is, the stiffer the spring is. In other words, the harder it is to stretch or to squish it a certain displacement x. So what will happen to a spring if we let it go? So let's say that this spring's equilibrium point is here. We lift it up a distance x, and then we decide to let it go. We decide to let go of the mass and just see what it does on its own. Well, it gets down to here, and you would think, well, if it gets back to equilibrium, then it's going to stay there. But it turns out that there's still some velocity on this object when it gets down to this point, so it's going to pass through equilibrium until it gets down to here, and the restoring force becomes large enough to bring it back up, and then it's going to bring back up. But again, when it gets here, it still has velocity. It's not going to come to a stop, so it's going to go on through that point until it gets up here, and then it's going to be pushed back down and then pushed back up, and then you get the picture here. So what type of curve does this look like? You may recognize it from math class. It's a, well, in this case, it's a cosine curve, but it could also behave like a sine curve. So it'll behave, oops, need to learn how to spell the word behave. Behaves like sine or cosine. Okay? So we have a special type of motion called simple harmonic motion. And simple harmonic motion exists when an object has a restoring spring force. In other words, it has a force equal to negative k times x, and if that is true, then that object exhibits what's called simple harmonic motion. It behaves like either a sine or a cosine. Now, I want you to write down all of these variables here. Yes, I do. Yeah, I know that you don't know what these are yet, but that's exactly what I'm going to go through on the next few slides here. I will tell you that x is our displacement from equilibrium, just like this x is. It's the same x. And x is a function of time, t. So that's what I put over here. X is a function of time. So time plays into this, and that this is where time shows up in our function here. And then you can write it as sine, or you can choose cosine. Either one will work. So let's talk about what all those other variables mean. Well, the first variable that we come across is what's called a. This is a multiplication constant out in front, and it is what's called the amplitude. The amplitude is the maximum distance that the object will travel away from its equilibrium point. So if you were to take a snapshot of the mass when it's at its highest distance and measure the distance from there to equilibrium, you would get the amplitude A. Likewise, if you were to come down here and measure its lowest distance from equilibrium, you would also get A. And then again, likewise up here, A, and so on and so forth. So A is as far as our object will travel away from equilibrium. Now our next variable, capital omega, and I should make a note of this here, so why don't you go ahead and do that too. This is capital omega. Just like in the Latin alphabet, we have capital letters and small letters. We have capital and small letters in the Greek alphabet too, and this happens to be the capital letter omega. Now, this capital letter omega is what's called the angular frequency. Now, this angular frequency is how many radians the spring will move on its graph in 1 second. What do I mean by that? So, we start off at 0 radians right here. This is what 0 radians, this is where it is at 0 radians. And then if I were to let time elapse for 1 second, let's say in that 1 second I go from here down to here. So after 1 second the mass has moved all the way from its highest point down to its very lowest point. So let's say it does that in 1 second. Well, then I ask myself, okay, how far has it moved in radians? Now, when you go from where you started all the way through 1 cycle, that is 2 pi radians. So, if I go from where I start halfway through my cycle, I have gone pi radians through my cycle. So, I would say, in this case, if I got to here after 1 second, then my angular frequency omega is 1 radian per second. Now if I were going twice as fast and got all the way through a complete cycle in 1 second, then I would say that my angular frequency is 2 pi radians per second. It's a similar principle to angular speed that we worked with when we were talking about circular motion. But now you have to think of radians in terms of not on a circle, but now you have to think in terms of radians on a sine or cosine graph. Now what I want you to do with this is I want you to write this down as you see it. And what I'm going to do when we come back tomorrow, or when we meet in class, excuse me, whenever that is, I am going to use this as our concept questions. So the concept questions will involve coming to this page and answering these 4 questions. Now, you can answer right now just by looking at this formula. You can answer this question. So for a stiff spring, remember that's large K. So when you have a large value K, what does that do to omega? Does that make omega large or does that make omega small? You can actually put that right here in this blank. And then let's say that we have a large mass, M. Well, if the mass M is very, very large, what does that do to omega? Does that make omega large or does that make omega small? I want you to write that in the blank right here. So you can answer those 2 questions right now. The other 2 questions we are going to answer when we get into class tomorrow, right after we answer some concept questions. And then we'll know a little bit more about what angular frequency looks like when we're actually looking at a spring moving up and down. But for now, just copy these down, and then tomorrow we'll fill them in. Now there are some other things, other terms related to angular frequency that you're going to run into when you are dealing with simple harmonic motion on a spring. One of those things is called period. And period is the amount of time it would take us to complete one complete cycle. So to go from its start point, go through a complete cycle and return to its start point. However much time that takes, that would be our period T. And we have a formula right here that gives us a relationship between omega, or angular frequency, and our period T. Another term that you're going to run into is what's called frequency. Now, frequency is the number of cycles you complete in a second. Angular frequency is the number of radians you complete in a second. But frequency is the number of whole cycles you complete in a second. So if in 1 second I were able to complete 5 of these cycles, 1, 2, 3, 4, 5, then my frequency would be 5 cycles per second. There's also another unit we also use when we talk about frequency, and you may have seen this one in certain places. It's called a hertz. So a hertz is 1 cycle per second. You may have seen that like on your radio or something like that. You might see kilohertz and megahertz. Well, that's talking about thousands of cycles per second in the case of kilohertz, and millions of cycles per second in the case of megahertz. Well, we're never going to see a spring go that fast, but that's probably where you've seen it the most often is on your radio. There is a relationship between this frequency and period. They are just reciprocals of one another. So F is equal to 1 over T. And then if you solve for T, you're going to get T equals 1 over F. And then there's also a relationship between frequency and angular frequency. Now, this is the relationship right here, but if you forget this relationship, just remember that here you have cycles per second, and then if you remember that there are 2 pi radians in a cycle, well, that means you have to complete 2 pi radians per second if you're going to complete 1 cycle per second. Another way to think of it is just to do a unit conversion between cycles and radians. Radians, there we go. Radians up there. That's another way to think of how to do the conversion between frequency and angular frequency. Okay, now we have one last variable in here in our equation, and it's given a Greek letter phi, P-H-I, phi, and that phi is what's called the phase shift. Now, all that a phase shift does is that it shifts your graph of amplitude, displacement versus time, and that's exactly what this is. It's a graph of displacement versus time. Time is along this axis, and displacement is along this axis. All it does is that just shifts this graph horizontally along the time axis. Okay, so to illustrate it best, I've given 2 examples here. I've given a red graph where x is equal to a times cosine of omega t plus 0. So in other words, this has a phase shift to 0. Now let's see if this makes sense. So when omega times t equals 0, we know that cosine of 0 equals 1. So yeah, that should be at its highest point right there. Okay, and then when omega t gets to pi over 2, it should go down to 0, which it does. And then it should go all the way down to its very minimum at omega t is equal to pi, and then 3 pi over 2, it should come back up to 0. Alright. Well, what if I replace 0 with negative pi over 2? Well, what that's going to do is that is going to actually shift our graph by pi over 2 radians to the right. So if omega t, if it was a maximum and omega t equals 0, now it has to be a maximum where omega t minus pi over 2 equals 0. Well, if omega t minus pi over 2 is 0, that means that omega t has to be pi over 2. Okay? So, if you were given a phase shift, and you're wondering where in the world do I start this graph, the best thing to do to ask yourself is, okay, where is this thing going to equal 0? This thing in parentheses. Well, that thing in parentheses is going to equal 0 when omega times t is equal to pi over 2. So you go to where omega t equals pi over 2, and you will start your cosine graph there. And then you can draw your graph from there. Okay. Another way to think about it is that notice that negative phase shift moves the graph to the right. So negative phase shift moves to the right. Positive phase shift moves left. Now, for those of you who are in advanced physics, we're not going to really use this much. We're not going to worry about phase shift all that much. But I need to put it up here for you because there are going to be some equations where you're going to see this phase shift phi. And those are equations that I have to show to the AP class as well. And they have to work with phase shift more. So you're going to end up seeing that phi, but I want you to just understand where it comes from and what it does. But we're not going to be needing to worry about it very much at all. So I just want to make you aware of it. Okay, I think that's everything for lesson 7.2.1. And I look forward to seeing you in class when we can do some problems around figuring out what amplitude is, what angular frequency is, period, and finally phase shift, especially for those of you in AP. Alright, look forward to seeing you soon. Bye.